Here we see a modified Atwood machine. We've got two pulleys. One of them is able to move, the other is stationary. We're given the masses of two blocks, 5 kilograms and 3 kilograms. And what are we asked for? We're asked to find the acceleration. So this is a perfect system for using a system of equations that we find using Newton's second law applied to each of these blocks. And the tool to set up those Newton's second law equations is, of course, the free body diagram. We can label our masses here. This is 5 kilograms. This is 3 kilograms. And now let's draw our free body diagrams. Here I have mg acting down. It's 50 newtons, but I'll call it m1g. And acting upward, we have tension. How many strings are in this question? Well, the only one that matters is this one here, describing this serpentine shape. And so we'll have that tension occurring throughout that rope. It's the same tension everywhere because these pulleys are frictionless and the rope is massless. For our second mass, we have acting downward, m2g, which in this case we know is 30 newtons. And acting upward, we have that tension not once, but twice. So that is it for our two free body diagrams. For the two masses that are free to move, the two free bodies in this system, hence the name, adding up the Newton's second law forces, the net force on block 1 is T minus m1g. Why am I not just putting in these numbers here? Well, I like to keep this symbolic for as long as I can because it helps me to check units, and it also makes the problem more general. I can check it with limiting cases of different masses. That's equal to m1a. I'm going to take up to be positive, so I'll write my forces as positive when they are upward. 2t minus m2g equals m2 times its acceleration. Now we need to be careful here. I've defined this symbol, a for acceleration upward of this block, and let's consider what will happen if this block moves up, say, 2 meters. If this moved up 2 meters, where would that 2 meters of rope end up? It would end up dropping this pulley by a certain amount because half of that rope would end up here and half would end up here. It'd have 1 meter on each side. And so the acceleration of this block would be half as much as whatever the symbol A represents, and importantly, it would also be in the opposite direction. That's our system of equations. I have two moving objects, and I have two unknowns, the tension and the acceleration. This is important. We need to end up having two linear equations here in our system of equations, and two unknowns, so we know right away this is solvable. Now I see that I have this system of two equations. I know that the thing linking the motion of block 1 and block 2 is the tension, so I should be able to eliminate it from the two equations relatively straightforwardly. I know that when I have a t in one equation, I should be able to match it with some number of negative t's in the other equation. So let's see, how could we approach that from a linear combination viewpoint? I think that I can multiply this bottom equation times -2, and that should help me clear this denominator and give me something with no fractions. And that would give me -4t here, so I'd like to multiply the top equation times +4. Let's apply that and multiply through. First equation becomes 4t minus 4m1g equals 4m1a. Multiplying through by a negative number here, I see that I can reverse the order of terms here. So I'm going to have 2m2g minus 4t equals positive now, and canceling the 2, positive m2a. So we have perfect alignment in taking a linear combination of these equations now. I've got a plus 4t and a minus 4t, so those will cancel. So we have, factoring out, a 2g m2 minus 2m1. I see that I distribute the 2 there and end up with this 4m1 equals, adding these equations together, m2 plus 4m1. All times are factored out a, so the acceleration in this system will be 2g m2 minus 2m1 over m2 plus 4m1. Checking our units here, it makes sense that we have a sum of masses in the denominator because the acceleration will be inversely proportional to some property of the total mass of the system. We have a multiplier here because of the mechanical advantage of the system that we have increased the acceleration of the right-hand side at the expense of the acceleration on the left-hand side relative to the right-hand side. I also see that I have a ratio of kilograms over kilograms with all of my m terms here, and g is out here by itself, which obviously has the units it needs to have to be an acceleration. Now it's straightforward to plug in our numbers, 3 and 5 here, and figure out what this acceleration will be. I see that it will be 20 times 3 minus 5, 3 minus 2 times 5 over 3 plus 4 times 5. So that is 20 times negative 7 over 23. So that's negative 140 over 23, or about 6.1 meters per second squared. And it is negative, telling us what? Since we defined the symbol a to mean the acceleration upward of block 1, we know that actually block 1 will accelerate downward. That's what we're told by that negative sign there for the acceleration. And as expected, it is a number between negative 10 and positive 10. We could not have an acceleration in excess of gravity in a system like this, where gravity is the only external force. We're also asked for the tension in the rope. How do we figure that out? Well, we just substitute this value for A back into the original equation. So T is equal to m1g plus m1a. m1 is 5 kilograms, so that's 5 times 10 plus negative 6.1. So the tension T is equal to 5 times 3.9 meters per second squared, or 19.5 newtons. Now, does this make sense? Let's see, since this block weighs 50 newtons and we know that it's going to accelerate downward, we know that the tension needs to be less than 50 newtons, which in fact it is. Since block 1 moves down, we know that block 2 must be moving upwards, which means that 2t must be more than 30 newtons. So t must be more than 15 newtons, which it is. So this all checks out. So just based on that consideration, we knew that t needed to be a number between 15 and 50, and we have confirmed this makes sense.